Greetings, everyone. Welcome to the 253rd session of the online Optom Learning Series OOLS. And for today's session, we have with us Dr. Rebecca Weng. Dr. Rebecca has obtained a Bachelor's of Optometry degree and a graduate certificate of ocular therapeutics from the University of New South Wales. She's also graduated with an MBA and also held a graduate diploma of interpreting and translation from the University of Western Sydney. She is currently associated with Manicon as the Profession Strategy and Service Manager for the Greater China region. And recently, she was also appointed as the member of Manicon's Global MTO Professional Service team. She has a past experience working with the Brian Holden Vision Institute, and she's a fellow of the British Contact Lens Association. She has also served as the project director for the International Myopia Institute prior to joining Manicon. She has a vast interest in managing patients with myopia, irregular cornea, doing clinical trials, and also fitting patients with contact lenses. She's involved in a lot of clinical trials which involve myopia control devices, contact lenses, and care products. And she extensively publishes case reports, scientific literature in international and national journals, presents in international and national journals as well, and reviews scientific publications for her time, what she has left with. So today she's going to take us through a very interesting topic on how do we decode something on myopia control, how can we apply the theories, what we learn from the research article into clinical practice. So thank you, Dr. Rebecca, for joining us today, and I'll let the screen time to be yours.
Thank you very much, Fakirating, for that nice introduction. Hi, everyone. I wanted to thank Online Optom Learning Series and Fakirating for having me today. I'm really excited to share with you on some of the update findings of optical methods that are used for myopia management. I also felt that understanding the hypothesis of the series behind all these interventions are critical in guiding us to select the treatment modality and looking at the published studies with an analytical mind. So first off, this is an infographic from the International Myopia Institute. It is published in 2023. So it's not the newest one. There's a newer one going to come up soon. This infographic, I do urge you guys to take a look, and it's good to put in your practice as well, because it did highlight the increase in prevalence, risk factor, and association with sight-threatening complications with myopia. As every one of you know, that myopia has become a critical public health concern, with prevalence rates surpassing 80% among the young adults in East Asia. Now, as I mentioned today, we are going to look at the optical methods, including spectacle lenses and contact lens options, with a touch on the combination therapies. Now, these are some newest findings since the publication of these infographics. But first, let us visit the basic theory behind these optical approaches, which would help us to understand why some of the current design works and what can we do to improve the myopia control intervention of this approach. Now, so first we have a poll question. So it's generally to understand what kind of myopia control interventions are you using currently in your practice.
I'm going to end this and share the results. So I think almost 70% of the attendees do have myopia control spectacles to their benefit, I would say, in helping patients, and then followed by orthokeratology. Some people do also are involved in combination therapies, contact lenses, and a couple of them probably have not started myopia control yet. Yeah.
That's excellent. I think today's talk will tie very close in what majority of you guys practicing already. So I do hope you can take away some key messages from today's presentation. Now, so it will go with the agenda flow as shown here. So what you'll see here is we will talk about the peripheral defocus theory first. We'll talk about the evolution of the theory. and how it's applied in modern day optical intervention approaches, and what's the known efficacy, and what can we do to improve that existing efficacy. And then we'll move on to the high order aberration theory. I feel this is quite new to us because during my optometry days, high order aberration, we only know that name, but we don't really know how it is measured and how our brain process that high order aberration and translate into an image that we can see. And also then I wanted to talk about some research linking high order aberration to the myopia control efficacy of all these different methods. And then I want to move on to the new optical design leveraging on this theory. And then move on to the third theory, which is the contrast sensitivity theory. We're talking about the mechanism and how we apply them clinically and what's the outcome. And then lastly, I wanted to quickly dive in some most updated studies that compares Orthok with myopia control spectacles. So this is today's agenda. Let's start with the first one, which is the peripheral defocus theory. Now, with the peripheral defocus theory, I'm pretty sure every one of us is very clear about this concept. So you can see from this particular diagram here is that when you put a glass lens in front of your eye, we're actually imposing a myopia defocus. That is, the focal point is projected in front of our retina, and our eye is guided by this optical message. So when it is projected in front of our retina, our eye will tend to grow towards that focal point. So this creates a more hyperopic eye shape. And this is what we call, when we impose myopia, a plus lens, it will create a hyperopic response. And conversely, if you put a negative lens, we're actually shifting that optical focus behind our retina, creating an elongation message for our eyeball, and therefore the eye become myopic. And this has been proven in animal models. And as you guys can see here, the red dotted lines is to show that when we put negative lenses, which is the imposed hyperopia on the eye, the vitreous chamber tended to grow longer. So the eye is becoming more myopia. And when we put that plus lens in front of our eyes, the vitreous chamber is shortening up. So the lens is not as long as when you put negative lenses in there. Therefore, we concluded optically imposed refractive error produces predictable refractive error change in many animal species. And then move on to the second one, because with the first experiment, we're just simply placing a full field of lenses in front of our eye, right? So then we went to think, okay, how does it impact our vision if we only put this focus of lens onto our peripheral retina? So what happens is, this is a monkey. So the monkey wore some goggles, right? And in the center of the goggle, it is just planar lenses. There were no optical manipulation. But outside this 4 to 8 millimeter aperture, we start to put either diffuser. So when we put diffuser, the image become really, really blurred. We call it form deprived message to the eye. Or we try to put a minus 3D lens, which is what when we impose that image onto the back of our retina, right? As from our previous slide. So when we do that, the retina is deprived from clear message from the diffuser, or if you put a minus 3D lens, the retina will tend to go to that focal point, which is behind our retina. And this is clearly shown from this diagram here. So these are monkeys. And if you see this gray shaded zone, these are our control monkeys. So we didn't put anything in front of their eyes. We let them grow as naturally how they would progress. So the monkey usually started with moderate hyperopia. And 3 months onto their development, 3 to 4 months onto the development, the eyes will still be hyperopic, but there is an amyotropization process going on there. As you can see, the eyes start to getting less hyperopic. But with those monkeys who we put either the form-deprived lens diffuser or minus 3D lens, you can see they're getting more short-sighted, right? The eyeball elongates. And this is also shown here. This is the results from the form-deprived lenses on the peripheral part of the eye. And this particular line here shows that minus 3D optical defocus focus behind the retina. They all produce similar results. The eye elongate and the eye become myopic. Now, this is the second series. So we know that minus lens induce myopic, right? Myopia. And we also know that the peripheral part plays a more important role. Moving on to the third series. So with the third series, before we start to have the third series, with the previous two series, we already start to have products on the market. If you guys are familiar with Zeiss Smile Vision, that is a peripheral defocus lens. And this is based on the two series we just observed from the animal studies. And then from 2007, 2009, scientists start to explore, what about if we present simultaneous defocus lenses on our eye? How would our eye respond to it? So the very, very first experiment, what they did is they used this Fresnel prism and to create circular annular rings of different powers. So this particular diagram here, you can see is the ring of lens. This is the plus power. It's up to 20 diopters. And then the second ring is a minus 10 diopter ring of defocus power. And this just alternates. So you have one ring of 20 plus 20D, one ring of minus 10D, and another ring of 20 plus 20D, and another ring of minus 10. They just alternate, and we'll put them in front of the mammal set's eye. And so what we find is this is the alternate ring wearer of the mammal set, is that even though we had equal area of these different powers, the eye still tended to show a plus lens driven response. So it's moving more towards the most myopic defocus. The plus lens has created a myopic defocus. So the eye shortens itself up, right? So even though you're presenting it with two stimuli, but it's moving towards where the plus lens is. And then we change the power to plus 10 one ring and minus 10 one ring. So these are equal power now. And you'll still find the monkeys who are wearing those lenses, they still show a most myopic focus driven response. So they still end up to be like a hyperope rather than a myope. And we kept on changing the alternate rings. So the ring then start to get more myopic. It's a minus 10 with a plus 5. And the eye was very close to being planal rather than a minus 10 response. And then we keep on increasing. And then the next lens was a planal lens, alternated with a minus 10 ring. And the eye wasn't minus 10, it was a minus 4. So you can still see that the planal, which is the most myopic focus ring of this lens, has more effect on how the eye developed. So this showed us if we have different powers, the plus power also had a more of a say on how our eyes develop. What about if we change the area of defocus? So this is the next experiment, which is quite fun. So they had plus 10 and minus 10 alternative rings, equal power, but different area ratio. As you guys can see here, it had one ring of minus 10 and one ring of plus 10. And in the next diagram, you can see they have increased the ratio of the minus 10. So it's now 33%, like it's 2/3 of the lens now, whereas the plus lens is only 1/3 of lens. We kept on increasing the amount of minus lens to a 25 to 75 ratio. So in this diagram, you would have a minus 10 in 75% of the lens surface, and only 25% of surface has a plus 10 ratio. And look at this result here. It's quite amazing too. So when they are equal, when you have plus 10, minus 10 of equal error ratio, our eyes still show a most myopic focus-driven response. So it went to the most plus lens. And then as we increase the ratio, still it's a plus 10 and minus 10. So now minus 10 occupies 2/3 of lenses, but our eyes are not minus 10. It was like a minus 6 change. So the plus lens still had the force to drive our eye growth. And as we increase, until we increase to that the lens is 100% of a minus 10 stimulus, then our eye become a minus 10 myope. But as you can see, so if we change the area of ratio, the area has a role to play. So maybe, based on this, we can find the optimum area ratio to create a sharp focus and the myopia control intervention method. This is the starting of dimmed lens by Hoya. I think this is how they started. When they experimenting with this such alternate rings, this kind of, screens back to that Hoya lens development. And then what happened is Smith, they repeat the experiment with monkeys again. So what they did with this particular experiment is they had control group of monkey again. And as you guys can see, they start with a moderate hyperb monkey, right? And then start to get a mild hyperb. So there's an emmetropization process going on with monkey as they start to grow older. Now, if we put this particular lens, it's a 50-50 area ratio, which means they had the same amount of area with both plus and the plano lens. And we want to see how the eyes develop. Now, in this experiment, 50% of that ring in total is a +3 diopter power, and 50% of that power is in plano power. And we can see most of the monkey, they are staying with that hyperopic lens, with that plus lens. So it's guiding the eyes going to the most myopic focus area. And at the end of the treatment, so what happened is this group is the normal monkey, and this blue group is when you give them like a +3 diopter lens, full field. There's no alternate rings, full field. So you can see that full field has the effect of them. So the eyes were getting more hyperopic. But if we did the alternate ones with a +3 diopter and a plano lens, it had an equivalent effect. So again, it confirms the experiment we just mentioned before, that the refractive development was dominated by the most positive power portion of the lenses. Now, repeating the experiment with monkeys again, and this time they test the area ratio as well. And as you guys can see, you should be very familiar with this now. They had, areas of 50-50% alternate rings of either +3D or plano lenses. And then they had a reduction of the plus lenses, right? This is 1/3 total area of the lens. They are +3 diopters, and 2/3 of the lens is plano. And we're just, moving on until that the +3D only occupies 18% of that lens. What we can see is, regardless of that area ratio, whether the +3D was getting smaller and smaller, you can see those monkeys, the red dotted ones are the monkeys that had a manipulation, they all remained much more hyperopic than the control group of monkeys. So this experiment is very, very good. It kind of said, hey, let's experiment and see how much surface area we can reduce to still have that myopia control effect without losing its efficacy. So all of this paved the ways for future spectacle lens development. And the last one is a very interesting one too. So all of this we're talking about now is about defocus theory, right? So this particular study against monkeys. And what happened is they tested, the peripheral, when we say peripheral defocus, how far does that peripheral defocus has to be for it to be effective? So with the first group, this is a monkey, we give them like a full 3 diopter positive lens in front of their eye. So it's just a +3D in front of their eye. And then they moved on to this group, the yellow group. What they did was they had the central part of the lens, without any manipulation, just a normal plano lens. And then beyond that 2 millimeter region zone, they had lens made of alternative rings, and which is +3D and plano, alternate rings of powers. And then with the green group, what they did is they expanded the central part from a 2 millimeter clear zone to a 4 millimeter clear zone. And then beyond that 4 millimeter, they had alternative rings of the +3D and plano powers. And then the blue group is when they expand that central zone to even larger area. So the central zone is now 6 millimeters without any manipulation. But beyond 6 millimeters, this is where they start to have the 3D and plano alternative rings of powers. And the last one is when they expand that optical, the very center zone to the 8 millimeter zone, where in the center 8 millimeter, they had no manipulation as well. But beyond that, they had same manipulation, which is an alternative ring of plus 3D and planar lenses. What we can see here is, if we just move on to this is the corresponding of that group. So from 2 millimeter, 4 millimeter, 6 millimeter, no, sorry, this is like, there's like full field. This is 2 millimeter, this is 4 millimeter. It seems to have a very, very positive effect. The eyes are getting more hyperopic, right? They are getting to the most plus lens area. But beyond that, when we dropped it down to 6 millimeters, it was still more hyperopic, but it was not as effective. And if you go to the 8 millimeter zone, which is really, really further beyond that, like really, really peripheral of the eye, the effect seems to be dropped even more. So what this tells us is a near to mid peripheral myopic defocus can slow down axial elongation. But if we apply defocus beyond approximately 20 degrees from the macula, it may not necessarily alter our refractive development. In other words, it may not be useful for myopia control, may not have the same impact. Now, when we talk about this peripheral defocus, to make it more concrete, I want you guys to have a look. So we have autorefractor, and we measure the refractive profile of the eye, right? This is the center of the eye. This is the temporal field of the eye. And as we expand, this is just more peripheral part of the eye. And if we expand this other part, is more nasal field, and it just expands more outside of our eye as well. So if you look at our emmetrope eye, you can see this line is fairly straight. So the eyeball is fairly spherical, I would say, and the focal point is always at the right spot, so you don't have any like myopic defocus or hyperopic defocus. Now, with a low myope, which is this line here, the dark navy line here, you can see it shows a U shape. So in the very center of our eye, which is the fovea, it is fully corrected, it's 0. But as we move towards the peripheral of our eye, the eye shows a hyperopia, some amount of hyperopia, right? That means the focal point is beyond our myopia, like our retina, it's beyond our retina. That's why it's showing a hyperopic response here. But if you look at hyperopes, just taking these two green lines here, this shows an inverted U shape, and it shows a minus response. That means our focal point is in front of our retina, and that's why it's showing this minus response. So in theory, what we're trying to say is, okay, emmetrope is like that, and our hyperope's profile is like an inverted U. So what we're trying to do is we're trying to move our myope, which is a U shape, the peripheral defocus U shape, into an inverted U shape. So this is what we're trying to achieve when we're trying to measure our peripheral refraction, and we say we have peripheral defocus. So if we look at the right graph, what we can see is this is a line. This is like just an imaginary patient of us, and they have a -2. They are a -2 myope, and shows a peripheral profile like a slightly straight line, inverted U, a U shape. And if you put a normal conventional contact lenses without any special design, it will show a similar shape. You'll correct the center part, it will be 0, but your peripheral part would still show a hyperopic response. That means your focal point is beyond your retina, so it will still stimulate your eye to grow. It will still become more myopic. So when you put ideally, when you put a myopic design lens, what you want to see is that inverted, oops, I'm moving too fast now, is you wanted to see this line. You want to see this particular U become an inverted U shape when you do measurement. That's what we're trying to do when we say, with a myopic design, we're trying to get more peripheral defocus power to control the elongation of the eyeball. Now, and this is true for also keratology, because with also keratology, what happens is, this is without Orthok, with this particular diagram, we just put our normal single vision negative lenses on the eye, And we can see the center of the eye, the focal point is always on the fovea, but the very peripheral light rays, they are always behind our retina. So it creates a hyperopic defocus, which will make our eyeball to elongate, it will grow towards that focal point. And when we put a ortho lens on our eye, because of that special molding of our eye, we have this particular mid-peripheral region, which has a plus power now. So what happens is all the light focal point, they're actually inside our retina. And so our eye will tend to grow towards that particular focal point. And by doing that, we are trying to control that eyeball growth. So this is how Orthok has been explained in the past. That's why it was slowing down the myopia, that it has a myopia control effect. And in fact, if you look at all those experiments where they try to measure the refraction at the different points of our retina, you can see it achieved that inverted U shape, right? Because normally it should be a U shape. We've achieved that inverted U shape. We wanted to achieve that controlling effect. And this is caused by, if we look at this is a topography map. So this is caused by this particular region here. So the treatment zone is where the red line is highlighting out, and it's this part here. So this is our correction zone where we compress our cornea to ensure that all the light rays, when they come in, they will focus on our retina. But this red ring here is where all the peripheral defocus start to working on. Actually, in fact, it started to work on from this part already. You can see there's a gradual increase. So it's not correcting myopia fully here. It was already placing that focal point in front of our cornea. And this is how we explain by how Orthok works. So we look at how early this line started to emerge. So the earlier, the better. It means that we start to have that peripheral defocus working in the very, very mid-periphery of our eye. And also, this is the full amount of the refractive power change. And the higher it is, the better it is for our eye as well. So in theory, if we wanted to have a really, really good myopia control effect, we want this to be a really, really pointy shape down here. So the very pointy, the very, very end point here is where your vision is crystal clear. It's fully corrected. And as we're moving down a little bit further out, this is where you start to have that uncorrected myopia there, but it's actually moving our focal point in front of our retina, and which is good for myopia control. And a lot of new design, or when people talk about Orthok, improving its efficacy, when they use a topography map, they simply look at that ring. They want that ring to be as small as possible. We want to squish as much towards the pupil as possible. And also this particular area, as we know, it's already starting to have that defocus amount as well. So we want as much squeezing to have a better effect. And that's what's happening with a lot of new design of Orthok lenses. Now with Orthok lenses, because it's known to be effective in controlling myopia to a certain extent, so there are a lot of study out there already. And that's why we can perform meta-analysis. Meta-analysis is by far the most statistical, powerful way to tell us how effective the treatment is and how reliable the results are. So when we look at this meta-analysis, it tells us that compared to wearing single vision spectacle lenses, that the patient who are wearing Orthok lenses, over a 2-year period, the actual elongation is about 0.5 to 0.8 millimeter less than the patient who don't wear Orthok lenses, who just simply wear single vision glasses. Now, in the past, we used to say, it's 45% more effective than the other method. But percentage has a letdown point, because we know that the younger children, they progress much faster, right? So if you let them wear a particular myopia control method, the percentage will not look as impressive as older kids, because with older kids, the myopia progression is not as fast. They might have a 0.1 millimeter growth in a year. And therefore, if you reduce it by 0.05 millimeters, that's a 50% efficacy. But imagine if you put them in our kids, our younger kids who are progressing, let's say 0.2 millimeters per year, and it was still reducing 0.05 millimeters for people who were also okay, then that efficacy is only 25%, right? But the absolute reduction here, this removes all the age factor away. We're simply comparing, okay, they are progressing, but how much less am I progressing compared to the single vision group? So for the rest of talk, you'll see in my, when I discuss about efficacy, I have both results listed, but I much like you to pay your attention towards that care, we call it care value. So that's the cumulative absolute reduction in actual elongation of this treatment compared to the single vision group or compared to the control group. So please remember this figure. So Orthok is effective. It reduces our actual lens by 0.5 to 0.25 to 0.28 millimeters over a 2-year period. Now, recently there are a lot of new study coming out where the researchers start to look at how can we improve the results that we already have. So we know it's effective, but it's effective only by 0.25 to 0.28. How can we make it more effective, right? So there are various methods with Orthok lenses. Now, all the study I pulled out, they use different methods to increase the treatment efficacy of orthokeratology. And they are all 2 years in study lens. They are all done on Asian kids. So this removes a lot of bias out in regards to those factors, how those factors would affect the result. Now, let's look at the first study. So the first study, they look at particular design of lenses. What they did is they increased the Johnson factor. Johnson factor is the compression factor of orthokeratology lens. So what compression factor does is we tended to overcorrect patients wearing orthokeratology lenses by a little bit. Why do we do that? Because our cornea will go back to its original shape as the day goes on, right? So, but we don't want patients to have perfect vision in the morning and then the vision deteriorates because the cornea starts to bounce back to its original shape. So that's why we tended to overcorrect the patient a little bit. So even though towards the afternoon, even though the cornea shape has started to bounce back, the eyes are still fully corrected. Now, with this particular experiment, what they did is they increased that compression, they increased that overcorrection by 1 diopter more. So they compress the cornea more, okay? And by doing that, I will talk about this more, they actually increase something. So, and that increased something, which we'll talk about, is actually the factor why it is more effective than a conventional design. Now, and then the second method they did is they tried to use a smaller optical zone. And as you guys remember, when we were talking about Orthok before, we said look at topography map. We want as much of the red ring going into the pupil center, right? So some of the experiments showed that if we reduce that optical zone diameter, then the treatment zone diameter, that ring, it will become smaller. It will get into our pupil a bit more. So that's one way of increasing the efficacy. And the third one is, okay, let's not manipulate Orthok. How about if we use combination therapy, right? We still use the same optical zone diameter, but now what we do is we put 1 drop of atropine in. Let's see whether this improves the efficacy. Now, with this combination therapy, I think it works 2 ways. One is atropine works on a different pathway. We all know pharmacological have another pathway that will control myopia. But secondly is when you put that 0.01% atropine, it enlarges our pupil, right? When you enlarge your pupil, that means more of the red ring can get into the pupil as well. So optically it works as well. So now by using all these 3 approaches, what we found in the study is it increases the efficacy by 0.17 to 0.20 millimeters. So remember, when we use the conventional design, when we don't do any change, the Orthok was already effective in reducing our actual lens by 0.25 to 0.28. Now we are adding another 0.17 to 0.20 on top of that, which means people wearing this improved approach of Orthok treatment, they would have a 0.4 to 0.5 millimeter less actual lens elongation compared to people who wear single vision, right? So it is a lot more effective if we try to manipulate the osteokeratology by either increasing the Jensen factor, by reducing optical zone size, or have it with atropine, like a combination therapy. But do be aware, all these ortho-K lenses, right? Even though we say ortho-K lenses are similar, they have optical zone, they have reverse zone, they have alignment zone, but the design do vary a little bit. So when we talk about those studies, it's in particular with this particular design that it works. With other design, it might work differently. So this is something I do want you to remember. Now, let's move on to that spectacle lens part of this myopia intervention, where majority of your practices, right? So we talk about ortho-K, now we'll move on to the myopia control spectacles. Now, by far the two hottest, I would say, spectacle intervention are the DIMS lens and also the Stellest lens. I'm pretty sure all of you guys are very familiar with this. Now, with Hoya lens, they had multiple lenslet with a plus 3.5 diopters of defocus lenslet in the lens center. And in the very center of the lens, it is manipulation-free. It's just a 9mm clear zone with the patient's original prescription. Now, with Stellest, they have 11 rings of aspherical lenslets of different powers. And in the center, they had similar, it's a 9mm zone as well, clear zone without any manipulation. So what I did was I looked at the 2-year efficacy of these lenses. In all these presentations, I will try to talk about 2 years rather than 1 year or like a prolonged period of time, because this is how you judge, how you can make comparison with all the treatment, right? So also, okay, we had a 2 year. Now, so with spectacles, even though now they have even 6 years results, I'm still using the 2 year results first, and I'll explain to you why I have a little bit of concerns about the 6 year results. So with the HOLT design, which is Stellest design, the 2 year results show that if we just look at the absolute reduction of actual lens compared to the single vision group, it's quite effective. It's about 0.35mm less actual lens growth compared to single vision. And DIMS lens, very similar, 0.34mm less than the single vision group, right? So they're very, very similar in efficacy if you look at the 2 year results. And you can also have a look at percentages. That's why I try to avoid using percentage, because the patient they recruit might be at different time as well, different time period and different age. So that's why I feel that if we use the cumulative absolute refractive elongation lots are much more robust comparison parameter. Now, moving on to 6 years, they have 6 year result, 5 year result for both lenses. The reason why I don't want to talk too much about it is because now we know that the spectacle lens have an effect on myopia control. So it will be unethical to leave our control group on single vision lenses, right? So all those control group, they will be moved onto the HOT lenses or DIMS lenses. So then how did they get the 6 year results? Well, they used a virtual group. So what they do is they go, okay, in the past, if we just put patients onto single vision lenses, and if they wear them for 6 years for this particular age group, the eyes would have grown that much. And compared to that virtual group, then our lens is about 0.6mm less growth. So it is a virtual group. It is not a head-to-head comparison in that sense. And unfortunately, nowadays, we just won't get any of those head-to-head results anymore, because it's unethical to leave your patient on those single vision lenses when you know there are much more better treatment to control their myopia. So remember these values as well. So we had also K with 0.25 to 0.28, and with enhanced result, which is 0.4 to 0.45mm over 2 years. Now the spectacle lens is about 0.34, 0.35mm less, right? So they're all very effective in another word. What about myopia control soft contact lenses? There are so many designs out there as well, even though we're still at the beginning of developing those different designs. But what I want to bring you to your attention is, so I think we know about the MiSight lenses, right? We call them dual focus lenses. And if we just look at the profile, this is a power profile of the lenses. So what you see is in the center, this flat part here, it is the patient refraction. It's the refractive error. So what we use to correct the refraction. And then you have this ring with plus powers. And this is why you see a peak on this part here. So it's showing you, okay, this is the power, this is the minus power, and then we put a ring of plus power, and then you can see a dip again. So the dip again is the patient original power. Then another peak, and that's a plus power. So you can see it's a very distinct annular ring of power change, right? And this is our MiSight lenses. And nowadays we also have other lens, which is that we have the Bloomday, and which is essentially the natural view lenses. And they use the technology called extended depth of focus. And what you can see is in the middle of the lens, a correctional vision, and then there's a slowly increase in the plus power, right? It's almost like a multifocal lens, a very slow increase in the plus lens, and then drops down again to your correction power. So you can see it's a smooth transition of the plus power in there. And then another type of extended depth of focus lens is the seed lenses or Mach and Novi lenses. They are this diagram here and this diagram here. So what you can see is it's very similar in terms of the architectural construction. So you always correct the center part, and then you have a gradual change, a plus power as you move out, and then you drop down again with your refractive power. So it is a very similar concept in terms of that if you look at those power profile. And then also there's the Johnson & Johnson Ability daily disposable lenses. And what you see here is they have a very small zone of plus power, so small that apparently it's not affecting our central vision that much. And then you have a patient's corrective power, then another small peak of plus power. So understanding all of this design tells how this optical construction of contact lens is manipulating the image in front of our eye. And there are results published as well. And we know MiSight has been on the market for quite a length of time now. And you can see here, usually I only put down the results of 2 years, or maybe, and here I put 3 years as well, because by 3 years, they still have that single vision contact lens control group. And I feel that those data are more robust in that. So you can see in the 2-year treatment compared to single vision contact lenses, it has a absolute reduction of 0.21 millimeters. So in other words, the actual lens was 0.21 millimeters less than that single vision control group. And if you move on to 3 years, the effect accumulates, right? Now it's 0.32 less than that single vision group. And then you look at that extended depth of focus design contact lenses, natural view and Milo, you can see that over a 2-year period, it's about 0.14 to 0.17 millimeter less actual lens elongation compared to single vision. Still effective as well. And with the Johnson & Johnson results, unfortunately, I only have the 6 months result I can find. And you can see that over a 6 month period, it's effective as well. The actual lens elongation is about 0.11 millimeter less than the control group. So all the design works, and it's too early for us to say which design works better. But as you can see so far, I think Orthok still, if we do some manipulation with Orthok, it still shows the strongest result when it comes to myopia control effect. Now, with all those different methods we talked about, we used peripheral defocus or simultaneous defocus as its backbone to say why this lens work, right? But now there's a new series coming out, surfacing out in recent years, and this is the high order aberration series. To start off why it works, I wanted to go through what is high order aberration. Now, aberration of our vision, like an eye, we also term as wavefront aberration. So our human visual system at its most fundamental level is a contrast sensitive detection system. So the quality of any optical system is judged by its ability to transfer information from observed object to the formed image. So if we can see that image very clear, then we will transfer to our retina as a very clear image, and then our retina will send a signal to our brain saying, look, it's very clear, and this is what we perceive. Now, an increasing aberration, as you guys can see here, there's a different kind of high order aberrations, and we are presenting that eye with a point source, a point dot source, okay? So with different high order aberrations, the point dot source is no longer point. You can see it's coming out different blurriness or doubleness or glariness in our vision. So it impacts our visual quality. And then, it kind of is related to our satisfaction about our vision as well. So what do we mean when we say it's a wavefront aberration? So how do we actually measure all of this image we see, right? So simply put, if we put a bundle of light rays going to our eye, and if our optic system, that is our cornea, our lens, our entire ocular system is very smooth, it's faultless, then the wave will go in as how the smoothness and of our eye is. So it will converge into one dot. But if our ocular system is not smooth, it's wavy, it's got imperfection in it. So when there's message coming to our eyes, we will see it as imperfection. And then if we measure, the retina will reflect it out as imperfection as well. So the image will come out as any of those letters you see here. It's not a crystal sharp E as we see here. So this is basically the fundamental knowledge of what wavefront aberration is. Now in our eye, it has two types of aberrations. One is what we call low order aberration. And this is something we really understand. What we mean by low order aberration, it is myopia, so when the image is not focused well, and hyperopia, same thing, or astigmatism. These are classified as low order aberration, and it counts 90% of the wavefront aberration our eyes experiences. Now, the rest of the 10% aberration is what we call high order aberration. This is where the little minor imperfection comes into our eyes, into our ocular system, and makes the image not so perfect anymore. And they can come in many, many names and many forms. So spherical aberration is one, coma is one, trefoil is one. And so all of this will cause our image not coming as sharp. And one thing I think is interesting to know is that out of the 10% high order aberration, 98.2% of those high order aberration comes from the front surface of cornea. So that tells us how important a good smooth cornea, a good quality, optical quality of cornea is to our vision, how much it contributes to sharp vision for us. Now, what is the impact of this high order aberration, right? So we understand it, there's 10% of that coming from the high order aberration. So how do they impact us? So basically, when we have a large amount of high order aberrations, it will cause us to have blurred or hazy vision in lower light condition. Lower light condition can be at nighttime, can be on rainy days, and will make it very difficult for us to read the fine prints or distinguish small details. And in turn, it will make our eyes very tiring when we try so hard to see the image. And this is a picture of keratoconate patient without any correction and with a 6mm diameter. And this is when the patient is corrected for their myopia or astigmatism. You can see the vision is still not that great. One thing with high order aberration is when you have a smaller pupil, actually will help with reduction in that high order aberration. It will make our vision better. So if you look through a pinhole, then your vision is much better than looking through a full field of view. The same patient, they're wearing spectacles, but the pupil is much smaller, and you can see that the vision is much clearer. And this is when they wear like RGP lens and scleral lenses with wavefront guided optics. So the vision is perfectly clear. So this is when both high order and low order aberrations corrected. Now, with high order aberration, they can come in different forms, okay? We don't need to go very details in this, but what I circle out in the red is basically the low order aberration. And the blue part is the high order aberration. And you can see I circled spherical aberration and coma out. This is how they're presented in like a visual format. These have been found to be affecting the treatment of our orthokeratology lenses. So just quickly go through this. So spherical aberration is like when you start to see halos. So when an image is haloic, and this is caused by the central cornea shape change, okay? Now, when we talk about coma, so these two are very common in osteokeratology. When you talk about coma, so this is point source appear like comet streaks, and this is what's causing double, like you see image doubling and blurred. And this is usually caused by the lens being decentered. So the shape of our cornea is a little bit different. Now, when we talk about also K lenses, we essentially compressing the center part of the eye, right? So the center part of the eye has less refraction, whereas the middle peripheral part of the eye has more reflective power. So when you look at this picture has a spherical aberration of 0.09 micrometers, and you can see the vision is pretty good. But as we move on to a increased amount of spherical aberration, we can see that 20/20 line is no longer that clear anymore. And if we increase that to 0.8 micrometers, that vision is really blurry when you have that amount of high order aberration, even if your myopia is fully corrected. So what happens with our eye is, in our human eye, we naturally have a slight amount of positive spherical aberration, okay? But when we wear Orthok lenses, it increases that spherical positive spherical aberration. So I just want to quickly touch on this. So when we have no spherical aberration, when we present a very clear image on our eye, retina sees it clear, the brain sees it clear. When we put a blurry image onto our eye, or maybe not so blurry, but our eye is not, let's say it's myopic, so the retina perceives image as blurry, and this transfers to our brain as blurry as well. Now, when we talk about spherical aberration, we already said the eye naturally have a little bit of aberration within itself. And if it's within the tolerance range, within our tolerance range, even though the image, when transferred to our retina, it's not crystal sharp, but because it's within the tolerance range, our brain will interpret as a sharp image, okay? Now, but if that amount of spherical aberration went too much, it's outside of our tolerance range now, then our brain will see it as a blurry image. So it tells us, we can have a bit of spherical aberration, and our brain will still see it fine, but when we exceed that tolerance amount, our brain will tell us, no, it's not good. I cannot see it clearly anymore. So with the Orthok lenses, what happened is, actually, before I talk about that, is I do want to revisit spherical aberration. So what we know is that the human eye can tolerate up to 0.6 micrometers of spherical aberration and still think that the image is clear. And when you go outside 0.6 micrometers, the brain will no longer cope with it and say it's not clear anymore. Now, we also know that spherical aberration is related with contrast sensitivity. So the more spherical aberration there is, the less contrast we can see. And this in turn gives us bad visual quality as well. So what happened is with also keratology, very, very early on, apart from that defocus theory, some scientists start to investigate the optical aberration caused by our Orthok lenses. What this study showed was they actually measured the optical aberration and showed that, hey, the myopia control effect from also keratology may be associated with factors beyond peripheral defocus theory. The high order aberration may have a role in controlling the myopia, progression. And moving on to this study, so it's another study. So a few years later, that is done by Professor Pauline Chu, and she combined all her Orthok lens studies, and she found that spherical aberration and also coma and total high order aberration probably does have an effect in slowing down myopia control with all this Orthok correction. And then, so what she did was she did increase that Johnson factor we mentioned earlier. And by increasing that Johnson factor, she measured the high order aberration. It increased high order aberration by 40%. And that has shown to slow down that myopia progression for that group with the increased Johnson factor. So in this study, she said she's concluding that myopia control effect is probably associated with high order aberration. At the same time, there were also other studies going on as well. As I said, there were smaller treatment zone area, and a lot of people say, when you have a small optical zone, it induces smaller treatment zone, and then it squeezes more defocus power into it. But in this particular study, they reduced optical zone by 0.5 millimeters, not much, but they didn't find any difference in terms of that defocus power created by the smaller optical zone. And similarly, another study, they didn't measure the defocus amount, but they did measure the high order aberration. So they had the optical zone reduced by 1 millimeter. And what they found is the smaller optical zone actually created much more high order aberration. So in other words, multiple studies trying to show, hey, the also keratology in terms of how it controls myopia control, maybe it's not solely dependent on defocus amount, the peripheral defocus amount, but also high order aberration might play a role in this. Just quickly go through this study. This study looks very complicated, but it's actually essentially a study look at the Orthok K group. So row A is all about Orthok K group. Row B is this myopia control and soft contact lens group. And within these two groups, what happened is they measure the peripheral defocus amount. And as you guys can see, that defocus amount between the two eyes are very similar. But with that soft contact lenses, they had a defocus amount of up to 20 diopters. So you can see far outside the very peripheral part of the eye that had much more defocus power. At the same time, they also measured the aberration, the high order aberration as well. And what they found is the Orthok K produced a lot more high order aberration between the two groups. So in this study, what they found is, okay, the myopia control soft contact lenses, although it was designed to mimic Orthok K lens, the myopia control effect was not as good as Orthok K. There was a statistical difference. So you can see, it's about 0.08 millimeters more elongation compared to the Orthok K lens. And they raised the question, it was very obvious that Orthok K produced more HOA. So maybe it could be related to that. At the same time, that much amount of hyperopic, that much amount of plus lenses in the periphery, is it creating too much defocus that's exceeding the retina's ability to actually understand where it's guiding it wrong? And also, is it too far out of the eyes as well? So that's why that could all be the reason that this lens is not performing as well as Orthok K, even though it's designed based on a similar theory as the Orthok K lenses. So this is a really interesting study. What they did is they look at lenses with multiple lenslet, right? So the top lenslet, they had lenslet of plus powers, plus 3D, whereas the bottom has minus 3D. So you would think, hey, with minus 3D power lenslet, the eye should grow more, right? Based on our previous simultaneous defocus theory. But amazingly, the interesting result was, regardless whether the patient is wearing the plus lenslet or the minus lenslet, both lenses had the same effect in slowing down myopia progression. So this leads us to kind of question, so what is the reason behind it to driving down that myopia progression? So what the study researchers said was they think that it could be that with both lenses, it caused a high order aberration. That is the main driver behind the myopia control theory. And they were saying that unlike these traditional lenses, these lenslet ray iris keep vision slightly imperfect everywhere, okay? It scrambles light in a way that makes the image always slightly irregular, and no matter where the eye focuses. So they suggest that a structured visual disturbance could be the key in controlling myopia, and this is what high order aberration comes in, rather than that defocus theory. I think that high order aberration plays more of a role, just to say maybe when we do something, when we make the object not too perfectly focused, yet not outside our threshold range, this would have some guidance to our eye, say, hey, maybe you don't need to grow any longer, stay in that particular parameter. Now, moving on to the very last series, the contrast sensitivity series. So I think most of you probably would already be aware that there's a lens called dot lens out in the market that uses this contrast series to explain why it works. So the contrast series states that the high artificial contrast environment overstimulates our retina, and this will lead to an overstimulation of our eye growth and myopia progression. It makes a lot of sense because think about our modern day environment. There's a lot of artificial contrast created by our modern day devices. So for example, that iPhone, iPad, a lot of high contrast environment, artificial contrast environment there. Modern skyscrapers, where everyone's crowded in this very crowded area, and also black prints on all white papers. Right. So if we read a lot, you just focus on that high contrast environment, it tends to provide you that stimulus for the eye to grow longer and to become more myopic. Whereas if we look at natural contrast, so when we say natural contrast, it refers to lower contrast stimuli. And, this actually would signal the eye to slow or stop growing. And that's why we say, spend outdoors, go outdoors, and their experiment, they actually painted a classroom with this low contrast environment, like a natural environment, to see whether that has an effect in slowing down our eye progression. Now, looking at how it is applied, in real world. So this is the dot lens. So what you guys can see, it doesn't look pretty, right? It looks quite interesting. So it has a 5mm aperture in the middle of the lens, and then the rest of the lens is dotted with a lot of micro diffusers. So by having those micro diffusers in front of our eye, it reduces that contrast, the contrast what our eyes are seeing. And we can see these are the results of this experiment. So this is already being tested and used on patients. So they had 3 groups. So the green group is the control lens, just the normal single vision lenses. Then they had test 1, test 2. Test 1, test 2, they're both similar lens design. Only with test 2, the dots are much more denser. So it's reduced the retina stimulus even more. And the patient wore the lenses for 1 year, okay, first. So you can see if they wear these lenses, the K value, which is the cumulative absolute reduction elongation. So compared to that single vision lenses, the eyeball was about 0.1mm less elongated. And with the test type 2 was 0.1mm. And you see why? Because it's more denser, it's more lower contrast. Why would it be like not as optimal as test 1? Well, the reason being it was so dense, the patient didn't like to wear them. So the wearing time was reduced and there were a lot of dropouts. And that's why it didn't work as well. So by the 3rd year, they start to move everyone, the test, not everyone, they start to move a test 2 because there's so many dropout into test 1 lens. And you can see it's a continuous effect. So a 4-year cumulative absolute reduction is 0.2mm less than the single vision group. Now, the study was done during COVID time as well. So there might be some factor influencing these results too. But you can see this is effective as well. So the contrast theory seems to be working too. Now, to conclude this presentation, there are a few more slides. But what I want to do is I wanted to actually show a few recent studies, a comparative analysis of ortho lenses versus myopia control spectacles, because they are the two most widely used optical methods in the market now, especially in the Asian market. So just a few summaries from International Myopia Institute. This hasn't been published, but this was reviewed on the IMC last year in Hainan. So what they did is they tried to see how different optical approach have any impact on our reading speed, stereopsis, and rebound effect. So what they found is with the new generation myopia control spectacles, that is Stellest dimmed lenses, the held lens may reduce reading speed, okay, and the dims and then the multifocal the myopia control soft contact lenses, they significantly reduce reading speed. However, with Orthok actually improves reading speed in children. So these are a few things that's worth considering if you have a patient coming and you're thinking, what do I give to them, okay? Now, with stereopsis, what happens is DIMS and hold lenses, they have some initial but clinically insignificant reduction in stereopic vision. With myopia control soft contact lenses, minimal reduction. Also can actually slightly improve after brief adaptation. But with rebound, what you found is they haven't noted any rebound with hold lenses and peripheral spherical lenses as well. And they didn't note any of those in multifocal soft contact lenses, dual focus, or extended depths of focus lens design. Or some of the study did notice their rebound effect on also keratology, but some noted that there's no rebound effect. So all of these are worth keep considering. So when you decided to stop the treatment for a patient, please do be mindful. Should you re-intervene if something happened as well? And something they wanted to investigate more is they're thinking with also keratology. Obviously, because we started using also keratology very early on. So now we are actually exploring how to improve the myopia control efficacy, right? So for the studies I talked before, increased compression factor, small optical zone design, and combined with atropine therapy, this will increase its treatment efficacy. Now, with the newer generation of myopia control spectacles, what they found is everyone knows there are promising results, right? We did see the results. It's very promising. It does show an actual elongation reduction, both short-term and long-term. But what we do found is, regardless of which design, the wearing time has an impact on its efficacy. So the patient need to wear the lenses 13 hours, I think, at least, or maybe 14 hours. So the longer they wear, the more efficacy it is sustained. Also, there are limited duration of current clinical studies. As I said, there's no more control group anymore when it's beyond certain period of time. And at the moment, we still don't know the exact mechanism of this myopia control effect exhibited by the spectacle lenses. We have a lot of theory, but we don't know exactly which one is driving it. All we know is if we produce some imperfection in our visual system, it may help, right? So second last slide, what we're going to do is this comparison study, look at Orthok lenses compared with different optical lenses. And with this particular study, they look at Oakley lenses compared with DIMS lenses. So what they found is overall, both Orthok lenses and DIMS lenses are effective in myopia control compared to single vision lenses. DIMS lenses is not as effective as Orthok lenses, and that's statistically significant. But if you further divide them into low myopia, moderate myopia, and high myopia, it tells you more. So within the low myopia group, what you can find is there's definitely a difference between the single vision wearing lenses, the control group, and the DIMS group. So the DIMS lens is definitely more effective than the single vision. And also, if you wear Orthok is definitely more effective than single vision. So there's a treatment effect there as well. But if you look at the moderate myopia group, what you found is it shows that Orthok definitely has a treatment effect compared to single vision, and definitely has a treatment effect compared to DIMS lenses, okay? And also within those groups, those lenses are effective too. However, if you look at the higher myopia group, this is where the difference screams out. So if you fit high myopia with Orthok lenses, definitely it has a treatment effect. It's much more slower actual elongation, and it's also much more slow treatment elongation compared with DIMS lenses, and that's statistically significant. However, if you put them on DIMS, there were no treatment effect between DIMS and single vision. So DIMS was not effective when you with high myopia patient. So this study showed us, if Orthok is probably more effective than DIMS lenses. But then if you move on to this other study, which showed a combination therapy with both Orthok lenses and DIMS group. Now, the very dark blue bar is the Orthok lens group, The orange bar is also okay with atropine, so it's a combination therapy. And the red bar is our DIMS lens, and the light blue bar is the DIMS combined with atropine. So what you found here is, okay, definitely combination therapy is more effective than our Orthok alone or than our DIMS alone, right? You can see there's a statistical difference between the two. But if you then divide the group between younger group and older group, then you start to see a difference again. So if you look at the younger group, what happens is within that DIMS and also atropine, so you can only see there's a statistically significant difference between the orthokeratology plus atropine with the DIM lenses. So if you compare these two groups, Orthok plus atropine is definitely more effective than DIMS lenses, but then there's no significant difference between all other groups. But if you look at the older group, what you see is you see the same thing as a total, right? So you can see the atropine is definitely more effective than the treatment, just giving Orthok alone or just giving DIMS alone. So in other words, with older kids, if you wanted to have better treatment efficacy, it's probably better for you to add that atropine. But for that younger group, that addition of atropine probably doesn't give you that additional effect. So this is something you keep in mind. And with the younger group, you're probably looking at starting with Orthok. And if you really have to give them DIMS, maybe you have to give atropine. It's just not effective. And if we look at the third study here, which is another study that compared different types of Orthok lenses and different types of myopia control spectacles, and you can see the result shows that they're equivalent. So all of them are equal. None of them screams out to be better than the other. And the very, very last study is quite interesting as well. So with all these, the three studies I've mentioned about, they're all 1 year in length. This last study is a 2-year study period, a 2-year study period study. So what they looked is they compared the HAL lens, the Stellest, with our Orthok lenses. So what they did find out is there's significant slower progression with HAL lens than Orthok lenses for the younger group, both at the 1 year and at the 2-year time period. There were no significant difference seen in the older group. Then they used subgroup comparison, and they show that for the moderate myopia group, that Orthok lenses may slow down actual elongation more at the 2 years, which means has a cumulative effect. So long-term effect Orthok is better for those moderate myopia group. So to conclude today's talk, I want to say there's still a lot of unknowns. So we still don't understand the underlying mechanism for the myopia control effect. As I said, there are a lot of theory out there. They all seem to be working, but exactly which one dominates, we don't know. All we know is maybe a slight imperfection presented to our visual system may help control the myopia control, may have the myopia control effect. We also have a lot of long-term efficacy study yet. Since the myopia control field, although it's so popular and so hot at the moment, but it didn't start to be this. I suppose the actual looking at the myopia control started in about 20 years ago. It's only in the recent years it starts to become overwhelmed with lots of studies. So we still don't have a lot of long-term efficacy study for us to know whether long-term it's still effective. So that's something we want to find out. And also still at the moment, there's no standardized method for managing myopia in clinical practice yet. We know every patient is different. So we really need to consider, their lifestyle, how they're compliant, and the cost of treatment, especially with combination therapy. Is it going to make compliance even harder? Now you have 2 treatments. So these are the things we have to take into consideration. And also, we need to integrate in our own experience, our clinical evidence with that individual patient needs to curate that perfect treatment or management paradigm for that patient. Now, we also know that there's new design coming out, and there's more results about combination therapy, and they do enhance myopia control efficacy. But we still need long-term study, again, to understand how they work, whether they have rebound effects as well. And, when should we stop one of those interventions if it's combination therapy, right? And so we need to understand that how that practical implication of combination therapy would work in our clinical practice. So with that, I really want to thank you guys for staying with me for the last hour or so. And I'm really privileged to have that opportunity. And I want to thank our online Optom learning series for having me today.
Thank you, Dr. Rebecca, for kind of putting the entire myopia digest, I would say. And I know this is not a complete digest. We still have a lot of other studies. We haven't talked about soft lens multifocal today. We haven't talked about, other things as well, the light therapies. But thank you so much for putting all of the evidence, especially for orthokeratology and the soft lenses, the my sight, and also the spectacle lenses. That's something, and all the theories on which they work. So thank you so much for doing that for us today.
Thank you for having me, Fakrati. And I really thank you guys for staying online. I know it's very late as well for some of you. So I think I'm very lucky to have all of you guys listening.
No problem. We did talk a lot about orthokeratology today, and we did compare, we talked about compression factor, we talked about the size of the optical zones, we talked about, the decentration issues a little bit in terms of orthoke causing higher order aberrations and things like that. One of the earlier questions was, what was the age? Because you did mention the age of onset, myopia control has also some effect. So would you highlight a little bit on the age for fitting orthoke lenses, if there is any evidence or any thoughts over when should we start fitting our patients with orthoke?
Yeah, I think as long as you know that the patient will do as you're told, because we know also keratology is a type of correction you wear at night. So rigorous compliance, cleaning lenses, taking care of lenses is very important. So to have that patient reach into that maturity, understanding that, when you tell them how to clean lenses, how to take care of lenses, when they have symptoms, when they have to stop wearing lenses, if they have that maturity to follow or to have that compliance as you guide them through, then I think you can fit them as young as 6 or 7. But in some other country, I know they have this mandatory lower age. So in China, for example, we start at 8. So we don't fit any kids that's younger than 8. Because we kind of concluded, hey, maybe 8 years old is when they are mature enough, or they can start to comprehending what to do. I suppose the parents plays a significant role when it comes to myopia management, regardless of which approach you use, because you need the parents to be there to remind the little patient that now it's time to wear your glasses. Now it's time you wear orthoke. Hey, if you have symptoms, you let me know. Are you cleaning your lenses as what's instructed, right? And are you replacing your lenses? So it is patient maturity, I would say.
Yeah, right. I think it's not just choosing the best. I mean, we know that there's so many options, as you mentioned. We still don't know which one will work best, but I think patient education and parents education is something which has to tag along with whichever option you choose, right?
Yeah.
Okay. And some thoughts about the higher order aberration, because we know by certain techniques, the dot lenses and the dot lenses for contrast sensitivity, of course, and for orthoke specifically for higher order aberrations, it does help, and it helps us to control myopia.
Mm-hmm.
Are there any implications towards peripheral vision when the kids are playing sports, or does it affect night vision? What are the long-term effects? Are there any evidence-based studies, if you are aware of, or your opinion about how this could affect a child's peripheral vision in sports or night vision, perhaps?
Yeah. In terms of long-term effects, we don't have any studies yet, but you'll be amazed just with the short-term study how adaptable kids are. So, with any of the treatment method we mentioned about, the amount of peripheral defocus or the amount of high order aberration created none of the kids had problem. They went through all the study period, and they are okay with lenses. They don't have any subjective symptoms. As an adult, I wear orthotic lenses for a while, and I can tell as an adult we're much more sensitive to the effect of that defocus and the amount of high order aberration. So when I was wearing my orthotic lenses, whenever I go to cinema or if I go to a museum or like a darkened museum room, I cannot see that clear, and it really annoys me as well. But with kids, they have no problem. They're very happy with what you're given to them. Yeah, but it will be interesting to investigate the long-term effect, whether it decreased their sensitivity, I suppose, to see things. Yeah, it'll be interesting to investigate.
Right. Yeah. As we say, like, kids don't complain too much. You just need to give them an ice cream. I heard this somewhere, can't remember where I heard this, but some people say, when it comes to myopia, remember ice cream. So you just give an ice cream to the kid, they won't complain, but an adult keeps complaining throughout their life for the smallest reason if their vision is not sharp. So
exactly.
So you can get away a lot with it. Yeah.
Yeah. We grow to be more picky, I suppose. Yeah.
That's right. Yeah. Yeah. And just your thoughts, just taking that last question. I mean, we didn't talk about a lot of things. One of it just came up on the chat on red light therapy. Any thoughts about red light therapy would you like to share? I mean, in terms of what do you think? Because I know this is a hot cake thing going on. There are differences in opinion, but we would like to know if you have some comments on that.
Yeah. So red light therapy is like a controversial topic, right?
Yeah.
So, I mean, we know there's published study, there's numerous study now saying it's effective. So we know it's effective. But also because it's so new in the market, there's different laser beam that's being used in the red light. So you can see from the very beginning where we were avoiding to talk about it because we don't know what's going on with this particular treatment therapy. Now it's evolved to setting up standard of what kind of red light laser beam we can use for the eye to have that effect. So there are definitely standard being set up to investigate what is the safety level and what sort of laser beam can we use for the kids. There are adverse event happening, and I've heard from anecdotal stories. So some of the damage in some kids, unfortunately, maybe is irreversible in some of the individual cases. So yeah, unfortunately, the case exists. That's why we're still investigating. How safe? What's the level? Can we really do that 3 minutes staring at that red light, for twice a day? Can we reduce that frequency? Can we reduce that red light beam? So these are all things that's being investigated. But I do see it being very, very good in terms of preventative measure once they have that standard, because they've already had study investigating whether it prevents myopia onset. It shows to be effective. So I think with both atropine and red light therapy, if they can be proven to be effective in preventing myopia onset, they will be much more effective than you give kids special design glasses to prevent myopia. Because, you are saying you are preventing you're delaying the onset, but the kids may eventually still have some myopia, right? So, they're going to wear glasses. So why put them on a pair of glasses when they're not myopia, right? So for me, I feel like using spectacle glasses to delay the onset of myopia, in real world, I don't know. There's pros and cons because you're putting them in the inconvenience of wearing glasses. But if you look at the atropine and red light therapy, you're not adding anything onto the daily life. So this, I would think it would have much more value, if that works. So this is my opinion of red light. So I do like to see more study on whether it has any preventative measures in delaying myopia onset.
Right. Yeah, we still have to wait for that evidence of long-term effects and how it can be used for preventative measures. Yeah, that's very well put. I think that's why we need to have. I mean, I can tell you that I think Dr. Rebecca will also agree. Myopia is such thing where every day there are not one or two papers published. There is double, triple digits of publications which come out with new information and comparative studies. And now, as Dr. Vega said, meta-analyses are now started to come up, combining studies and giving more information. So we are still learning, and I hope that in a couple of years, I think we'll have more idea than what we have today.
Yeah, exactly. I would like to have more guidance on, okay, with this particular patient, you put them on ortho, or with this, you start them with spectacle lenses. This would help a lot, right? Rather than us, okay, I think right now we know they all work, but we know they are non-responders. So it's still trial and error, unfortunately, right? For the first 3 or 6 months, unfortunately. So I would hope that we have more guidance on what's the best for our patient. Yeah.
Right. And just before we end, Dr. Rebecca, would you like to share anywhere which everybody could go and read more about the latest information? Is it the IMI guidelines? Is your to-go website, or are there some other website if you'd like to share?
Yeah, so for me, I love to use the IMI website, the International Myopia Institute website. They have they have 3 series of papers out now. So basically summarize all the key papers in the field, and they are all tested. They're tested and picked by the task force group. So if you're looking for some information, these are by far the most trusted resources to look at, and it kind of they are like 20 pages long. But once you have read it, you will become an expert in that particular area. So for me, this is definitely my go-to. Even though we're still waiting for the next lot of series, there's a newer. I think there will be a new updates coming up soon. So if you want to look for newer updates, what I suggest is if you're interested in like myopia control spectacle lenses, you just type into PubMed. PubMed is a great resource. If you type those keywords, and there'll be new studies coming out, and you can read it. And once you read it, there'll be reference part to other studies as well. So PubMed is another resource I use quite frequently.
Wonderful, great. So I think thank you so much, Dr. Rebecca, I know it's early morning already, I think, for you in Australia. So thank you so much for staying up late and, doing this session for us and taking us through the key highlights and papers, giving us a lot of evidence-based results about myopia and leading the session today. So thank you so much for that.
Thank you, Thackeray, and thank you, Optom Online Learning Series, and thank you everyone for still staying online. I really enjoyed it, and it's my pleasure, to be here. So thank you for having me.
Most welcome. We do have some sessions planned over the next weeks. We will be sharing more details about them onto the social media and to your email. Until then, take care, be safe, and I hope to see you during the next session. Take care and bye-bye. Thank you, Dr. Rebecca. Bye.
Thank you. Bye.